Let me tell you about something that the world's space agencies know but rarely discuss publicly, truths so disturbing, so fundamentally challenging to the narrative of human space exploration that they're buried in technical reports, obscured in scientific jargon, and kept from the inspiring stories we tell about venturing into the cosmos. They know it's deadly. NASA knows, ESA knows, Roscosmos knows. Every space agency that has seriously studied long-duration spaceflight knows that deep space is not just challenging, it's lethal in ways we're only beginning to understand. And they know that the solutions we have are inadequate, that the timelines we're advertising are unrealistic, and that the astronauts we're planning to send face risks that haven't been fully disclosed. This isn't a conspiracy. It's not a cover-up in the sinister sense. It's something more subtle and perhaps more troubling, a systematic tendency to emphasize the positive, minimize the negative, and maintain public enthusiasm for programs that depend on that enthusiasm for funding and support. The truth about deep space is darker than the promotional videos suggest. The challenges are greater than the press releases acknowledge. The gaps in our knowledge are wider than the confident timelines imply. Let me take you through what NASA and other space agencies know but don't emphasize, the deadly realities of deep space that rarely make it into the public conversation. Let me start with radiation, because this is perhaps the most serious threat that space agencies consistently downplay. You've probably heard that radiation in space is a concern. What you probably haven't heard is how serious that concern really is and how far we are from solving it. Deep space is bathed in radiation from two sources: solar particle events and galactic cosmic rays. Solar particle events are bursts of radiation from the sun associated with solar flares and coronal mass ejections. They're intense but relatively easy to shield. Against a few centimeters of material can stop most solar particles. Galactic cosmic rays are different. They're the nuclei of atoms from hydrogen to iron and beyond, accelerated to nearly the speed of light by supernova explosions and other cosmic phenomena. They carry enormous energy and they penetrate almost anything. Here's what NASA knows but doesn't emphasize. We cannot effectively shield against galactic cosmic rays with any practical amount of material. The physics is unforgiving. When a high-energy cosmic ray hits shielding material, it doesn't just stop. It creates a cascade of secondary particles, neutrons, protons, pions, and other fragments that can be even more damaging than the original particle. Adding more shielding can actually increase the radiation dose inside the spacecraft as more secondary particles are created. To significantly reduce galactic cosmic ray exposure would require meters of material water, polyethylene, or other hydrogen-rich substances. The mass would be enormous, far beyond what we can practically launch. A spacecraft with adequate shielding might weigh thousands of tons, orders of magnitude heavier than anything we've ever sent to deep space. NASA's own studies acknowledge this. The technical reports are clear. Galactic cosmic ray exposure during a Mars mission cannot be reduced to safe levels with passive shielding. The best we can do is minimize exposure time and accept the elevated risk. What is that risk? NASA estimates that a Mars mission would increase an astronaut's lifetime cancer risk by 5% or more. That's the number you sometimes hear. What you don't often hear is the uncertainty around that number and how it might be a significant underestimate. The 5% figure is based on models that extrapolate from studies of atomic bomb survivors and medical radiation patients. But cosmic radiation is different from the radiation in those studies. Galactic cosmic rays include heavy ions, iron nuclei, and other massive particles that cause a different type of damage than gamma rays or X-rays. When a heavy ion passes through tissue, it doesn't just ionize molecules along its path. It creates a dense track of damage, breaking multiple DNA strands in each cell it traverses. This cluster damage is harder for cells to repair than the diffuse damage from other types of radiation. The biological consequences may be more severe. Animal studies have shown concerning results. Mice exposed to heavy ion radiation show increased rates of cancer, cognitive decline, and other health problems. Some studies suggest the risk may be higher than the models based on atomic bomb data would predict. NASA knows this. The agency has funded extensive research on space radiation biology, and the results are sobering. A 2016 report from the National Academy of Sciences noted that the uncertainties in risk projections for space radiation carcinogenesis are large, potentially a factor of 2 to 4 inches either direction. This means the actual cancer risk from a Mars mission could be 20%, not 5%. It could be even higher. We don't know, and we won't know until we have more data that can only come from actually exposing humans to these conditions. But it gets worse. Cancer is not the only concern. Recent research has revealed that space radiation damages the brain in ways we didn't anticipate. Heavy ions kill neurons, disrupt neural connections, and cause inflammation in brain tissue. Studies in mice show cognitive impairment problems with memory, learning, decision-making, and emotional regulation. NASA has termed this space brain the gradual degradation of cognitive function from cosmic ray exposure. And unlike cancer, which might take years or decades to develop, cognitive effects could emerge during the mission itself. Imagine astronauts on Mars, 225 million kilometers from Earth, with radiation-impaired cognition, slower reaction times, impaired memory, poor judgment. In an environment where a single mistake could be fatal, this is not a minor concern. NASA's public communications mention radiation as a challenge being addressed. The technical literature tells a different story. Radiation is a fundamental barrier that we do not currently know how to overcome. Now let me tell you about what NASA knows about the health effects of microgravity and what they don't tell the public. You've probably heard that astronauts lose bone and muscle in space, and that exercise helps counteract this. What you probably haven't heard is how inadequate the countermeasures really are and how permanent some of the damage may be. Astronauts on the International Space Station exercise 2 hours per day. They use resistance machines, treadmills, and cycling ergometers. This exercise regimen is more rigorous than most people on Earth maintain. And it's not enough. NASA's own data shows that even with intensive exercise, astronauts continue to lose bone mass about 1 to 2% per month in weight-bearing bones. Over a 6-month mission, that's 6–12% loss in critical areas like the hip and spine. What NASA doesn't emphasize is that this loss may not fully reverse. Studies of astronauts years after their mission show that some never regain their pre-flight bone density. The skeletal damage from spaceflight appears to be partially permanent. The microarchitecture of bone, the intricate internal structure that gives bone its strength, can be destroyed by microgravity. When bone is rebuilt after return to Earth, the architecture may not be restored. The bones look normal on a density scan, but are structurally compromised, weaker than they should be, more prone to fracture. NASA knows this. A 2022 study in Scientific Reports involving NASA-funded researchers found that astronauts had not fully recovered their bone strength even a year after returning from the ISS. The press release was muted. The implications were stark. For Mars missions, the problem compounds. Astronauts would spend 6 to 9 months in microgravity traveling to Mars, then live in Mars's weak gravity 38% of Earth's for a year or more, then spend another 6 to 9 months in microgravity returning home. The cumulative bone loss could be catastrophic. Astronauts might return with bones so weakened that normal activities risk fracture. They might be permanently disabled by a mission to Mars. NASA's Artemis program aims to return humans to the moon and eventually send them to Mars. The program's promotional materials show astronauts bounding across alien landscapes. What they don't show is the medical tent that might be needed when those astronauts return to Earth. But bone loss is just one part of the picture. Let me tell you about what NASA knows about vision damage and how this problem caught them by surprise. For decades, astronauts reported vision changes after long-duration missions. NASA initially attributed these to normal variation or aging. It wasn't until the early 2010s that the agency recognized a serious systematic problem. Spaceflight-associated neuroocular syndrome, or SANS, affects a majority of astronauts on long-duration missions. The symptoms include swelling of the optic nerve, flattening of the eyeballs, and vision impairment. Some astronauts have returned from the ISS needing glasses for the first time in their lives. Some have suffered permanent vision loss. The cause appears to be elevated intracranial pressure from fluid shifts to the head. In microgravity, without the downward pull of gravity, fluid accumulates in the upper body and head. This increased pressure damages the optic nerve and reshapes the eye. NASA knew about this problem for years before acknowledging it publicly. The agency funded research, convened panels, and developed countermeasures, all while publicly maintaining that astronaut health was being managed successfully. Even now, NASA doesn't have a solution to SANS. The countermeasures under development, lower body negative pressure devices, specialized sleeping positions, potential pharmaceutical interventions, are experimental. None has been proven to prevent the syndrome. For a Mars mission, SANS could be devastating. Astronauts might arrive at Mars with significantly impaired vision, unable to perform tasks requiring visual acuity. They might return to Earth legally blind. NASA's technical reports acknowledge this risk. The promotional materials do not. Now let me tell you about what NASA knows about the brain and how recent discoveries have raised new alarms. MRI studies of astronauts have revealed that spaceflight causes significant changes to brain structure. The ventricles, fluid-filled spaces in the brain, expand substantially during long-duration missions. The brain itself shifts position within the skull. White matter and gray matter show measurable changes. These findings were published in scientific journals, but they haven't received the public attention they deserve. NASA has been notably quiet about the implications. The ventricle expansion is particularly concerning. In some astronauts, the ventricles have expanded by 25% or more, a degree of change that in other contexts would be considered pathological. And the expansion doesn't fully reverse after return to Earth. Each subsequent spaceflight adds to the cumulative change. What do these brain changes mean for cognitive function? NASA doesn't know for certain, and that uncertainty is itself concerning. Some studies have found subtle cognitive changes in astronauts, problems with processing speed, spatial reasoning, or emotional regulation. Other studies have found no significant impairment. The mixed results may reflect individual variation, differences in measurement techniques, or the insensitivity of current cognitive tests. What we don't know is whether these structural changes cause problems that emerge years later. Will astronauts who flew long-duration missions experience accelerated cognitive aging? Will they face higher rates of dementia or neurological disease? The data to answer these questions doesn't exist. The long-term follow-up hasn't been done. NASA is flying astronauts into an environment that causes measurable changes to their brains without understanding the long-term consequences. This is not disclosed in the enthusiastic narratives about Mars exploration. Let me tell you about another issue NASA doesn't like to discuss: the psychological toll of deep space missions. The ISS orbits about 400 kilometers above Earth. Astronauts can see their home planet through the window. They can communicate with mission control in real time. In an emergency, they can return to Earth within hours. A Mars mission would be fundamentally different. astronauts would be 225 million kilometers from Earth at maximum distance, so far that communication takes 20 minutes each way. They couldn't have a conversation with family or mission control, only exchange delayed messages. In an emergency, there would be no rescue. They would be on their own, utterly isolated for years. The psychological effects of such isolation are unknown. We have analogs, Antarctic research stations, submarine patrols, isolation experiments, but nothing truly comparable. No human has ever been that far from Earth, that cut off from humanity for that long. NASA's research suggests that serious psychological problems are likely. Depression, anxiety, interpersonal conflict, psychotic episodes all have occurred in isolated environments far less extreme than a Mars mission. How astronauts would cope with the reality of their isolation, the knowledge that no one could help them if things went wrong, is unknown. NASA conducts psychological screening and training for astronauts, but screening can only eliminate the clearly unsuitable. It cannot guarantee that selected individuals will maintain psychological health under unprecedented conditions. And once symptoms emerge, treatment options in deep space would be severely limited. The agency has funded research on psychological countermeasures, artificial lighting to maintain circadian rhythms, virtual reality for psychological escape, training in self-treatment, and peer support. But these are untested solutions to an unprecedented challenge. What NASA doesn't emphasize is that a psychological breakdown during a Mars mission could be catastrophic, not just for the affected individual, but for the entire crew and mission. In a cramped spacecraft with no escape, mental illness is not just a health issue, but a safety issue. Now let me discuss what NASA knows about the limitations of life support systems and why the confidence in our technology may be misplaced. The ISS life support system is an engineering marvel, recycling air and water, maintaining temperature and pressure, supporting human life in the vacuum of space. But it requires constant maintenance, regular resupply from Earth, and a robust ground support team monitoring it around the clock. On a Mars mission, none of this would be available. The spacecraft would have to operate autonomously for years. Parts would wear out that couldn't be replaced. Systems would fail that couldn't be repaired. The crew would have to diagnose and fix problems with limited tools, limited spares, limited expertise. NASA's own analyses suggest that the reliability requirements for a Mars mission far exceed what we've demonstrated. The probability of a critical system failure over a multi-year mission is not negligible, and a critical failure in deep space means death. The agency is working on more reliable, more autonomous systems, but the technology readiness is lower than the ambitious timelines suggest. We have never operated a crewed life support system for years without resupply. We have never sent humans beyond reach of emergency rescue. What NASA doesn't emphasize is that a Mars mission with current technology would carry a significant probability of mission failure resulting in crew death. The exact probability is debated, but it's not negligible, perhaps 5%, perhaps higher. Compare this to airline travel, where we expect a safety record better than 1 fatality per million flights. A 5% chance of death would be considered catastrophically dangerous for any other human endeavor. For Mars, we're contemplating accepting it as the cost of exploration. This calculus is rarely discussed publicly. The promotional materials show astronauts planting flags, not mission failure scenarios. The public is not being told the full scope of the risks. Now let me tell you about what NASA knows about the timeline and why the dates you hear are misleading. NASA has talked about sending humans to Mars in the 2030s. SpaceX has claimed even more ambitious timelines. These dates appear in presentations, articles, and public statements as if they were realistic projections. Internally, NASA knows better. The agency's own analyses show that the technical challenges remaining are substantial. The Space Launch System and Orion capsule, the hardware for lunar missions, are years behind schedule and billions over budget. The systems needed for Mars deep space habitats, landing vehicles, surface systems, return vehicles are in early development at best. NASA doesn't have a funded, integrated plan for a Mars mission. What exists are concepts, studies, technology demonstrations, the early stages of what would be a decades-long development program. The confident timelines are aspirational, not realistic. A sober assessment suggests that a human Mars mission might not happen until the 2040s or 2050s, if it happens at all. The technical challenges, the funding requirements, the political sustainability of multi-decade programs, all of these create uncertainty that the public statements don't acknowledge. The gap between public rhetoric and internal assessment is significant. NASA leaders speak optimistically because optimism generates support, which generates funding, which enables programs to continue. Honesty about the timeline might undermine that support. This isn't unique to NASA. SpaceX, which has made the most aggressive claims about Mars timelines, has consistently missed its own targets for other projects. The gap between Elon Musk's stated timelines and actual achievement is measured in years. The public is being given a misleading impression of how close we are to Mars. The reality is that no one alive today may see humans on Mars, despite the confident predictions. In part 2, I want to go deeper into what NASA knows about the specific dangers of deep space, the problems they've studied extensively but don't publicize. Because understanding what space agencies know but don't tell requires examining the technical literature, the internal reports, and the candid assessments that rarely make it into public view. So we've begun to examine what NASA and other space agencies know, but don't emphasize the radiation that can't be shielded, the bone loss that may be permanent, the vision damage that catches them by surprise, the brain changes whose consequences are unknown, the psychological toll that could be catastrophic, the life support limitations that create real risk of death. Now I want to go deeper into the technical details, the specific findings buried in scientific papers and internal reports that paint a picture far darker than the public narratives suggest. Because what NASA knows about deep space is more troubling than what NASA tells about deep space. Let me start with what NASA knows about solar particle events and why they pose a more immediate threat than most people realize. Galactic cosmic rays deliver a chronic, continuous dose of radiation that accumulates over time. Solar particle events are different. They're acute, intense bursts of radiation that can deliver a lethal dose within hours. Solar particle events occur when the sun releases massive amounts of energy in flares or coronal mass ejections. These events accelerate protons and other particles to high energies, creating a wave of radiation that can reach dangerous levels. On Earth, we're protected by the atmosphere and magnetic field. On the ISS, which orbits within Earth's magnetic field, astronauts have some protection and can shelter in the more shielded parts of the station during solar events. On the Moon or in deep space, there is no such protection. NASA knows that a major solar particle event during a Mars mission could be catastrophic. The largest recorded solar event occurred in 1859, the Carrington event. If a similar event occurred during a Mars mission, astronauts caught outside their spacecraft or in a poorly shielded location could receive a lethal radiation dose within minutes. Even inside a spacecraft, the exposure would be severe. Spacecraft shielding can reduce the dose, but cannot eliminate it. A Carrington-class event could cause acute radiation syndrome, the immediate effects of high radiation exposure, including nausea, vomiting, fatigue, and damage to the immune system and bone marrow. Acute radiation syndrome is not just unpleasant, it can be fatal. Doses above 4 to 5 sieverts cause death in most cases without medical treatment. Doses above 8 sieverts are almost invariably fatal, even with treatment. A Carrington-class event could deliver doses in this range to inadequately shielded astronauts. How likely is such an event during a Mars mission? NASA has studied this question extensively. Major solar particle events are associated with the solar cycle occurring more frequently during solar maximum, but they can occur at any time, and predicting them more than a few days in advance is currently impossible. Over a 3-year Mars mission, the probability of a major solar particle event is significant, perhaps 20% for an event requiring emergency shelter, perhaps 1 to 5% for a potentially lethal event. These are not negligible odds. NASA's response to this threat is a storm shelter, a highly shielded area where astronauts would retreat during solar events. But designing, building, and flying such a shelter adds mass, complexity, and cost. The trade-offs are challenging. What NASA doesn't emphasize is that the storm shelter concept is not fully validated. We've never tested a human-rated storm shelter in deep space conditions. We don't know how quickly astronauts could reach the shelter in an emergency. We don't know how long they could stay there, hours, days, if a prolonged event occurred. The public narrative presents solar particle events as a managed risk. The technical reality is that they represent a genuine threat of astronaut death that cannot be eliminated with current technology. Now let me tell you what NASA knows about the effects of space radiation on the cardiovascular system, a relatively recent discovery that has raised new concerns. For years, radiation research focused on cancer and cognitive effects. But studies over the past decade have revealed that space radiation also damages the cardiovascular system in ways that increase the risk of heart disease. Radiation damages the endothelium, the lining of blood vessels. It accelerates atherosclerosis, the buildup of plaques in arteries. It increases inflammation throughout the cardiovascular system. These effects contribute to heart attacks, strokes, and other cardiovascular events. A study of Apollo astronauts, the only humans who have traveled beyond Earth's magnetic field, found that they had significantly higher rates of cardiovascular disease than astronauts who stayed in low Earth orbit. The sample size was small, but the finding was striking. Deep space radiation appeared to increase cardiovascular mortality. NASA has funded additional research on this topic, and the results are concerning. Animal studies confirm that space radiation damages the cardiovascular system. The mechanisms are becoming clear. Radiation-induced oxidative stress, inflammation, and cellular damage all contribute. What this means for Mars astronauts is troubling. They would face elevated risk not just of cancer and cognitive decline, but of heart attacks and strokes, risks that could manifest during the mission itself or in the years afterward. NASA's risk models are still being updated to incorporate cardiovascular effects. The full scope of the risk is not yet quantified, but the preliminary data suggests it may be substantial, perhaps comparable to the cancer risk, perhaps greater. This finding has not been widely publicized. The cardiovascular effects of space radiation are discussed in technical journals, but rarely mentioned in public communications about Mars missions. Now, let me explain what NASA knows about the immune system and why this creates vulnerabilities that compound all the other risks. Space suppresses the immune system. This has been known for decades, but recent research has revealed the scope and mechanisms of immune dysfunction in ways that raise new alarms. Multiple factors contribute to immune suppression in space: stress, radiation, altered circadian rhythms, changes in the microbiome, and direct effects of microgravity on immune cells. The result is a weakened ability to fight infection, control inflammation, and detect and destroy cancer cells. NASA has documented that dormant viruses reactivate in astronauts' bodies during spaceflight. Herpes simplex, varicella zoster, Epstein-Barr viruses that most adults carry but that are kept suppressed by the immune system become active again. Astronauts shed viral particles in their saliva indicating active infection. This viral reactivation is concerning in itself, but it's also a marker of broader immune dysfunction. If the immune system can't keep dormant viruses suppressed, what else is it failing to do? The implications for long-duration missions are serious. Astronauts would face increased risk of infection from each other, from their spacecraft environment, from their own dormant pathogens. They would have reduced ability to heal from injuries or recover from illness. They would have impaired cancer surveillance at exactly the time when radiation is causing DNA damage. NASA's response has been to develop pharmaceutical countermeasures and improve monitoring. But these solutions are partial at best. We cannot fully restore immune function in space with current technology. What NASA doesn't emphasize is how immune dysfunction compounds other risks. The radiation damage that increases cancer risk is more dangerous when the immune system that would normally detect and destroy cancer cells is impaired. The cardiovascular damage that increases heart disease risk is worse when inflammatory regulation is disrupted. Every system affects every other system, and immune dysfunction makes everything worse. Now let me discuss what NASA knows about the psychological screening process and its limitations. NASA selects astronauts through a rigorous process that includes psychological evaluation. Candidates are screened for mental health history, personality traits, coping abilities, and interpersonal skills. The goal is to select individuals who can withstand the stresses of spaceflight. But NASA knows that screening has fundamental limitations. First, screening can only evaluate candidates under normal conditions. How someone responds to isolation, confinement, and danger in a testing environment may not predict how they'll respond when the isolation is real, the confinement is inescapable, and the danger is constant. Second, mental health can change. Someone who is psychologically healthy at selection can develop problems later from the mission itself, from life events, from the cumulative stress of the astronaut career. Screening at one point in time doesn't guarantee stability over years. Third, the unprecedented nature of deep space missions means we have no valid predictive models. No human has experienced what Mars astronauts would experience, the extreme isolation, the communication delays, the knowledge that no rescue is possible. We cannot predict how even the best screened individuals will respond. NASA's psychological research has identified concerning patterns in analog environments, isolated Antarctic stations, submarine patrols, chamber studies. Depression is common. Interpersonal conflict is common. Cognitive performance degrades over time. Some individuals experience more severe problems, paranoia, psychosis, suicidal ideation. In these analog environments, individuals can be evacuated if problems become severe. On a Mars mission, there is no evacuation. An astronaut who develops serious psychological problems would remain with the crew for the duration of the mission, months or years. The tools available to manage psychological problems in flight are limited. Pharmaceutical interventions, antidepressants, anti-anxiety medications, antipsychotics could be carried, but their effectiveness in the unique environment of deep space is unknown. Psychological support from Earth would be limited by communication delays. The crew would largely have to manage problems themselves. NASA has developed training programs for psychological self-care and peer support, but these programs are untested in conditions comparable to a Mars mission. Their effectiveness is assumed, not demonstrated. What NASA doesn't discuss publicly is the possibility of psychiatric emergencies during deep space missions, suicides, violence, complete psychological breakdown. These are low probability events, but over a multi-year mission with multiple crew members, they cannot be ruled out. The consequences could be catastrophic. Now let me tell you what NASA knows about the medical challenges of deep space and why the confident talk of treating injuries and illnesses in flight may be misleading. On the ISS, astronauts have access to a medical kit, telemedicine support from ground-based physicians, an emergency return to Earth if needed. Serious medical problems, appendicitis, heart attacks, major trauma can be managed by rapid return. On a Mars mission, none of these options would exist in the same way. Communication delays of up to 20 minutes each way would make real-time telemedicine impossible. Ground-based physicians could provide guidance, but the crew would have to execute any procedures themselves. Emergency return would not be an option. The orbital mechanics of Mars missions don't allow for rapid return. NASA has studied what medical capabilities would be needed for a Mars mission. The list is sobering. The ability to perform surgery, manage trauma, treat infections, handle cardiac emergencies, address psychiatric crises, and cope with a wide range of conditions that might arise over a multi-year mission. No spacecraft currently has these capabilities. The ISS medical kit is designed for minor problems and stabilization until return, not definitive care for serious conditions. Training crew members to handle medical emergencies is challenging. Astronauts are already highly trained in many areas. Adding comprehensive medical training competes for time with other essential skills. Even with training, crew members would not have the experience that comes from years of medical practice. NASA has funded research on autonomous medical systems, AI-guided diagnostics, robotic surgery, telemedicine protocols designed for communication delays. But these technologies are in early development. They are far from ready for a Mars mission. What NASA knows but doesn't emphasize is that astronauts on a Mars mission would face medical risks that cannot be adequately managed with current or near-term technology. Conditions that would be treatable on Earth could be fatal in deep space. The crew would be one serious illness or injury away from catastrophe. The probability of a medical emergency over a multi-year mission is not negligible. Appendicitis alone has a lifetime incidence of about 7%. Extrapolating from Earth-based data, the probability of at least one crew member experiencing a significant medical problem during a Mars mission might be 30% or higher. This is not a solved problem. It's a major gap in our capability for deep space exploration, a gap that NASA acknowledges in technical documents but doesn't emphasize in public communications. Now let me discuss what NASA knows about the spacecraft environment and the ways it can make astronauts sick. The closed environment of a spacecraft creates unique health challenges. Air and water are recycled, microorganisms circulate and evolve, contaminants accumulate. The environment that keeps astronauts alive can also make them ill. NASA has documented that the microbial environment of the ISS is distinct from Earth environments. Some organisms thrive in the spacecraft conditions, potentially becoming more virulent. Biofilms form on surfaces and in water systems, resistant to cleaning and disinfection. Astronauts on the ISS have reported respiratory problems, skin irritation, and other symptoms that may be related to the spacecraft environment. Air quality issues, including elevated CO2 levels and particulate contamination, have required attention. On a Mars mission, these problems would be amplified. The mission duration would be longer. Resupply would be impossible. The systems that maintain air and water quality would have to function perfectly for years without major maintenance. NASA knows that spacecraft environmental health is a significant challenge. The agency has invested in improved air and water purification, antimicrobial materials, and monitoring systems. But the technology for multi-year deep space missions remains undemonstrated. What NASA doesn't discuss publicly is the possibility of environmental degradation over a long mission, accumulating contamination, system failures, emerging health problems that can't be addressed. The spacecraft that sustains life could also undermine it. Now let me explain what NASA knows about the return to Earth and why this may be the most dangerous part of the mission. We've discussed the damage that accumulates during spaceflight, bone loss, muscle atrophy, cardiovascular deconditioning, vision changes, brain alterations. All of these reach their peak at the moment of return to Earth's gravity. NASA knows that returning astronauts are in their most vulnerable state when they need to be most capable. The landing itself may be challenging. Astronauts would need to operate complex systems while experiencing the full force of Earth's gravity for the first time in years. Their reflexes would be slowed, their cognition potentially impaired, their physical strength severely diminished. After landing, they would need to exit the spacecraft, potentially in an emergency situation. Astronauts returning from the ISS after 6 months sometimes cannot walk without assistance. After a Mars mission lasting years, the disability could be far more severe. NASA has studied what support returning Mars astronauts would need. The requirements are extensive. Medical teams standing by, equipment for extraction, facilities for immediate rehabilitation. All of this assumes a landing in a prepared location with ground support. But what if the landing doesn't go as planned? What if the spacecraft lands off target, in a remote location, or with damage that requires emergency evacuation? Astronauts who can barely stand might need to perform emergency procedures, survive harsh conditions, or await rescue that takes days to arrive. NASA's contingency planning addresses these scenarios, but the solutions are limited. The fundamental problem is that returning astronauts would be physiologically compromised at exactly the moment when they might need to be most capable. This is what NASA knows. The return to Earth is not a triumphant homecoming, but a medical emergency in progress. Every returning astronaut is, to some degree, a patient requiring immediate care. Now let me discuss what NASA knows about the long-term consequences, the health effects that emerge years or decades after missions. Space agencies track astronaut health, but longitudinal data is limited. We haven't been flying long-duration missions long enough to know the full consequences. The astronauts who spent extended periods on Mir and ISS are still being followed, but many haven't reached the age when health problems typically emerge. What data exists is concerning. Studies of radiation workers and atomic bomb survivors show that cancer risk remains elevated for decades after exposure. The same is expected for astronauts, but the specific risks from space radiation are poorly characterized. The cardiovascular effects observed in Apollo astronauts suggest that deep space radiation may accelerate heart disease. If this applies to all astronauts, we would expect elevated rates of cardiovascular mortality as they age. The long-term consequences of bone loss, brain changes, and other spaceflight effects are unknown. Some changes appear permanent, others partially reverse. The implications for aging and long-term health are unclear. NASA maintains a longitudinal study of astronaut health, but the sample size is small and the follow-up period limited. We won't know the full consequences of long-duration spaceflight for decades long after we've sent more astronauts into harm's way. What NASA doesn't emphasize is this uncertainty. Public communications present spaceflight as risky but manageable, with known consequences and effective countermeasures. The reality is that we're conducting an experiment on human health with an unknown endpoint. Now let me explain what NASA knows about the ethics of this situation and the uncomfortable questions that arise. NASA operates under ethical guidelines that require informed consent for human subjects research. Astronauts are informed of known risks and must consent to accept them. But how can consent be truly informed when the risks are uncertain? How can astronauts consent to long-term health consequences that won't be known for decades? How can they evaluate risks that even experts disagree about? NASA's ethics reviews have grappled with these questions. The agency has established frameworks for acceptable risk, distinguishing between risks that are known and quantified, risks that are known but uncertain, and risks that are unknown. But the frameworks don't eliminate the ethical tension. We're asking astronauts to accept risks we can't fully quantify, with consequences we can't fully predict, for benefits that are collective rather than individual. The comparison to other hazardous professions is imperfect. Firefighters and soldiers accept risks, but those risks are better characterized. We know the mortality rates, the injury patterns, the long-term health effects. For deep space exploration, we're operating with much less information. There's also the question of who bears the risk and who receives the benefits. Astronauts bear the health consequences. The public receives the inspiration, the scientific knowledge, the national prestige. Is this distribution fair? Are astronauts being adequately compensated for what they risk? These questions don't have easy answers. NASA acknowledges them in ethics discussions, but doesn't resolve them. The agency proceeds with human spaceflight because that's its mission, while managing ethical concerns as best it can. What NASA doesn't discuss publicly is the possibility that we're asking too much, that the risks of deep space exploration may exceed what we should ethically impose on any individual, no matter how willing. In Part 3, I want to explore what all of this means for the future of space exploration, for the astronauts who might fly these missions, and for the public that supports these programs. Because what NASA knows but doesn't tell has implications that extend far beyond the technical details. So we've journeyed through what NASA and other space agencies know, but don't emphasize the radiation threats that can't be shielded, the solar events that could be lethal, the cardiovascular damage newly discovered, the immune suppression that compounds every risk, the psychological vulnerabilities that screening can't predict, the medical emergencies that can't be treated, the environmental hazards that accumulate, the return to Earth that is itself a crisis, the long-term consequences that won't be known for decades. Now I want to explore what all of this means. What are the implications for the future of human space exploration? What does it mean for the astronauts who might fly these missions? And what does it say about the relationship between space agencies and the public they serve? Because what NASA knows but doesn't tell isn't just a collection of technical problems, it's a window into how we make decisions about risk, exploration, and the value of human life. Let me start by examining why NASA communicates the way it does, why there's a gap between internal knowledge and public messaging. NASA is a government agency dependent on public funding. Its budget is set by Congress, which responds to public opinion. To maintain funding, NASA must maintain public support. And public support depends on enthusiasm, optimism, and confidence in the program. This creates an institutional incentive to emphasize the positive and minimize the negative. Problems are presented as challenges being addressed. Risks are acknowledged but framed as manageable. Timelines are optimistic. The narrative is one of progress, achievement, and inevitable success. This isn't unique to NASA. All organizations that depend on public support tend to present themselves favorably. Politicians, corporations, nonprofits all engage in similar communication strategies. NASA is not unusually deceptive. It's normally institutional. But space exploration is different from other endeavors in important ways. The risks are extreme. The consequences of failure include human death. The public is being asked to fund activities that put people's lives in danger. In this context, the gap between internal knowledge and public messaging raises serious ethical questions. There's also a cultural factor within NASA. The agency was built on a foundation of can-do optimism. The Apollo program succeeded against enormous odds, largely because of this culture. NASA learned that believing in success helps create success. But this culture can also create blind spots. The Challenger disaster resulted partly from a culture that minimized safety concerns in favor of mission success. The Columbia disaster had similar roots. NASA has tried to learn from these tragedies, but institutional culture is hard to change. The astronaut corps itself reinforces the optimistic narrative. Astronauts are selected partly for their ability to project confidence and inspire the public. They're trained to represent the program positively. Expressing doubts or concerns about mission safety is not rewarded. This creates a system where negative information is filtered at multiple levels. Researchers publish concerning findings in technical journals that the public doesn't read. Program managers acknowledge risks in internal reviews that the public doesn't see. Public affairs officers craft messages that emphasize achievement over hazard. Astronauts speak enthusiastically about missions whose dangers they understand but don't dwell on. The result is a systematic gap between what NASA knows and what NASA tells. Now let me examine the specific ways this gap manifests in current Mars planning. NASA's current strategy for human Mars exploration is called the Moon to Mars program. The plan is to establish a sustainable presence on the Moon, learn to operate there, and use that experience to prepare for Mars missions. This is presented publicly as a logical, methodical approach. The Moon is a proving ground where we'll develop and test the capabilities needed for Mars. Each step builds on the previous one, reducing risk and building confidence. What NASA doesn't emphasize is how much remains unknown and how far behind schedule the program already is. The Space Launch System, the heavy lift rocket intended for these missions, has been in development for over a decade and has flown only once. The Orion capsule has similar history. The Gateway space station, planned to orbit the Moon, is in early development. The Human Landing System for lunar surface operations is being developed by commercial partners whose schedules have slipped repeatedly. The lunar surface systems needed for a sustained presence, habitats, rovers, power systems, resource extraction equipment, are largely conceptual. The technology demonstrations needed to validate these concepts haven't been conducted. And all of this is just for the Moon. For Mars, the additional requirements are staggering. Deep space habitats that can function for years, landing vehicles capable of reaching Mars's surface and returning to orbit, surface systems that can operate in Mars's environment, propulsion systems efficient enough for the round trip. None of these systems exist. Most are in early conceptual stages. The development timeline for Mars capabilities is measured in decades, not years. NASA's public communications imply steady progress toward Mars. The technical reality is that we're at the beginning of a very long road, with many unsolved problems and no guarantee of success. The timeline implications are stark. NASA has talked about humans on Mars in the 2030s. The technical reality suggests the 2040s or 2050s are more realistic if the program maintains political and funding support for that long. What NASA doesn't tell the public is that the confident timelines in presentations and press releases are aspirational targets, not realistic projections. The actual schedule depends on solving problems that haven't been solved, developing technologies that don't exist, and maintaining political will for decades. Now let me discuss the specific health research that NASA has conducted but doesn't widely publicize. NASA's Human Research Program has funded extensive studies on the effects of spaceflight. The results are published in scientific journals, presented at conferences, and compiled in technical reports. They're not secret, anyone can access them, but they're not featured in NASA's public communications. Let me describe some specific findings that illustrate the gap between research and rhetoric. A 2020 study published in JAMA Ophthalmology examined eye changes in astronauts. The researchers found that after long-duration missions, 52% of astronauts showed optic disc edema, swelling of the optic nerve, and 25% showed globe flattening, reshaping of the eyeball. These changes were associated with vision impairment that in some cases persisted for years after return to Earth. This study was funded by NASA and published in a major journal. It received some media coverage, but it's not featured in NASA's descriptions of spaceflight health management. The impression given is that vision changes are being addressed, not that half of long-duration astronauts suffer documented eye damage. A 2021 study in Scientific Reports examined bone recovery after ISS missions. The researchers found that astronauts had not fully recovered bone density even 1 year after return, and that some showed permanent deficits. The bone microarchitecture had been damaged in ways that didn't repair with time. Again, this NASA-funded study was published openly, but the implication that spaceflight causes permanent skeletal damage is not emphasized in public communications. The narrative remains that exercise countermeasures address bone loss, not that they're partially ineffective. A 2017 study in Nature examined brain changes in cosmonauts after long-duration missions. Using MRI, the researchers found significant redistribution of cerebrospinal fluid and measurable changes in brain structure. A follow-up study found that these changes persisted for at least 7 months after return to Earth. The implications that spaceflight causes lasting changes to the brain are concerning, but NASA's public communications don't emphasize them. The brain research continues, but the public impression is that neurological effects are minimal. These examples could be multiplied. Study after study has found significant health effects from long-duration spaceflight. The pattern is consistent. Effects are worse than previously thought, countermeasures are less effective than hoped, and recovery is slower and less complete than assumed. NASA knows all of this. The agency funded the research, received the reports, and incorporated the findings into its risk assessments. But the knowledge remains largely in technical circles, while public communications maintain an optimistic tone. Now let me examine how this communication gap affects public understanding and policy decisions. The American public generally supports NASA and space exploration. Polls consistently show positive attitudes toward the space program and approval of ambitious goals like Mars missions. This support provides the political foundation for NASA's funding. But what is this support based on? If the public understood the full scope of risks involved in deep space exploration, the radiation that can't be shielded, the health damage that may be permanent, the significant probability of mission failure would support remain as high. We don't know, because the public hasn't been given that information in accessible form. The enthusiastic narratives dominate media coverage. The technical reports that document the risks aren't widely read or reported. This creates a problem for democratic decision-making. The public is being asked to fund programs whose risks they don't fully understand. Elected officials are making policy decisions based on incomplete information. The normal process of informed consent, essential for medical research on human subjects, is attenuated when applied to an entire society. Some might argue that the public doesn't need to understand every technical detail. Space agencies have expertise that the public lacks. Delegating decisions to experts is appropriate. But there's a difference between delegating technical decisions and delegating value judgments. Whether the risks of Mars exploration are worth the benefits is not a technical question. It's a question about values, priorities, and acceptable risk. These are questions that should be decided democratically with informed public input. Currently, that input is based on incomplete information. The public thinks it's supporting a risky but manageable endeavor. The technical reality is that the risks are greater, the management is less effective, and the outcomes are more uncertain than the public narrative suggests. Now let me discuss what this means for the astronauts themselves. Astronauts are the individuals who bear the risks of space exploration. They're the ones who will experience the radiation exposure, the bone loss, the vision damage, the psychological stress. They're the ones who might die if something goes wrong. Astronauts accept these risks knowingly. They're extensively briefed on the hazards of spaceflight. They sign consent documents. They make informed choices to pursue this career despite the dangers. But how informed can consent really be when significant uncertainties remain? Consider an astronaut contemplating a Mars mission. They would be told about the radiation exposure and the estimated cancer risk. But they wouldn't be told the actual risk because it's not known with precision. They might be told the risk is 5% when the actual risk could be 10% or 15%. They would be told about the potential for cognitive effects from radiation. But they wouldn't be told whether they personally will experience significant cognitive decline because we can't predict individual responses. They would be told about the bone loss and the importance of exercise countermeasures. But they wouldn't be told that they might return with permanent skeletal damage because we can't predict whose bones will recover and whose won't. In each case, consent is given based on incomplete information. The astronaut agrees to accept risks that are described in general terms, but whose personal implications are unknown. This is unavoidable to some extent. All consent to future activities involves uncertainty. But the magnitude of uncertainty in deep space exploration is unusual. We're asking people to accept risks that we can't quantify with consequences that we can't predict based on information that we know to be incomplete. Is this truly informed consent? Or is it something else consent given in good faith based on the best available information but without the full understanding that the term informed implies? There's also the question of institutional pressure. Astronauts who express concerns about mission safety might find their careers affected. The astronaut corps is competitive. Raising doubts about program direction is not rewarded. An astronaut who publicly questioned NASA's readiness for Mars missions would likely not be selected for those missions. This creates a culture where concerns are minimized and optimism is rewarded. Astronauts who might have reservations about mission risks are incentivized to keep those reservations private. The public sees confident, enthusiastic explorers. The private doubts remain hidden. I'm not suggesting that astronauts are being coerced. They genuinely believe in the mission. They're genuinely willing to accept risk for the sake of exploration. But the institutional environment shapes how they express themselves and what aspects of their experience they share. Now let me explore what would happen if NASA were fully transparent, if the agency told the public everything it knows about the risks of deep space exploration. Imagine NASA holding a press conference where the administrator laid out the full scope of challenges. We estimate that a Mars mission would increase astronauts' lifetime cancer risk by 15%. We can't be more precise than that. There's a 20% chance of a solar particle event that would require emergency shelter, and a 1 to 5% chance of one that could be lethal despite our countermeasures. We expect astronauts to lose 30% of their bone mass and may not fully recover. More than half will likely suffer some degree of vision damage, some permanent. We don't know the long-term cognitive effects of the radiation exposure and brain changes we'll observe. The probability of a medical emergency we can't adequately treat is perhaps 30%. The overall probability of mission failure resulting in crew death is uncertain but might be 5 to 10%. What would be the public reaction to such candor? Some would appreciate the honesty. They would recognize that exploration involves risk and would support proceeding despite the dangers. Others would be horrified. They would question whether any goal justifies exposing humans to such risks. They might oppose further Mars planning until the risks are reduced. Political support would likely become more complicated. Some members of Congress might question continued funding. Others might demand that NASA focus on risk reduction before proceeding with ambitious missions. The overall effect would probably be to slow the program, reduce funding, and delay progress toward Mars. This is precisely what NASA fears and why the agency tends toward optimistic communication. But there's another possibility. Honest communication might actually build stronger support. The public is not stupid. People understand that exploration involves risk. They accept that some endeavors are worth pursuing despite danger. The astronauts themselves accept the risks. Why wouldn't the public support their choice? Honesty might also build credibility. If NASA acknowledged the full scope of challenges, the agency's claims about progress would be more believable. The public might trust NASA more, not less, if the agency were seen as forthright about difficulties. An honest communication would enable genuine public deliberation about whether Mars exploration should proceed, at what pace, with what safeguards. This is how democratic societies should make decisions about risky endeavors through informed debate, not managed messaging. We don't know which effect would dominate, whether honesty would reduce support or build it. NASA has chosen not to run this experiment. The agency continues with optimistic communications, maintaining support but at the cost of full transparency. Now let me discuss what this situation reveals about the relationship between scientific institutions and the public. NASA's communication gap is not unique. Many scientific and technical institutions face similar tensions between internal knowledge and public messaging. Climate scientists know more about the uncertainties in their models than public communications suggest. Medical researchers know more about the limitations of treatments than drug advertisements convey. Engineers know more about the risks of technologies than manufacturers disclose. In each case, institutions face pressure to present their work favorably. They compete for funding, public support, and political attention. Uncertainty and limitation don't generate enthusiasm. Confidence and achievement do. The result is a systematic bias in scientific communication, a tendency to overstate certainty, understate risk, and present progress as more linear than it is. This bias is not dishonest in any individual instance, but it accumulates into a distorted public picture. This has consequences beyond any single institution. When the public learns that risks were greater than acknowledged, when a drug has unexpected side effects, when a technology fails catastrophically, when a mission ends in disaster, trust in institutions erodes. The optimistic communication that was intended to build support ends up undermining it. NASA experienced this after Challenger and Columbia. In both cases, the agency had information suggesting elevated risk that wasn't effectively communicated. When the disasters occurred, NASA's credibility suffered. The gap between internal knowledge and public assurance was exposed. The lesson seems clear. Honest communication, even when it reveals problems, is better for long-term trust than optimistic messaging that later proves unfounded. But institutions find it hard to learn this lesson. The short-term incentives for optimism are strong, and the long-term costs of lost credibility are diffuse and delayed. Now let me consider the international dimension of this issue. NASA is not the only space agency pursuing deep space exploration. ESA, Roscosmos, CNSA, JAXA, and other agencies have their own programs and their own communication practices. These agencies face similar tensions between internal knowledge and public messaging. They compete for national prestige, funding, and public support. They have similar incentives to present their programs favorably, but there are differences. Some agencies operate in political systems where public opinion matters less than government direction. They may face less pressure to maintain enthusiastic public support, but also less accountability for how they communicate. The international competition adds another dimension. When China announces ambitious plans for lunar exploration, NASA faces pressure to match them. When SpaceX claims it will send humans to Mars within years, NASA's more cautious timeline seems inadequate. The competitive dynamic pushes all players toward optimistic claims. This competition is sometimes presented as beneficial, driving innovation, accelerating progress, spurring achievement. And there is truth to this. Competition motivates performance. The Apollo program was driven largely by competition with the Soviet Union, but competition can also drive excessive risk-taking. When success is defined by who gets there first, safety concerns may be minimized. The pressure to meet schedules can override the caution that safety requires. The history of spaceflight includes disasters that resulted from competitive pressure from the Soviet Soyuz 1 crash that killed Vladimir Komarov to the Challenger disaster that killed 7 Americans. In each case, the drive to meet schedules and maintain competitive position contributed to the decision to proceed despite known risks. As international competition in deep space exploration intensifies, this dynamic bears watching. The race to Mars, if it becomes a race, could create pressure to accept risks that cooler assessment would reject. Now let me explore what might change this situation, what forces could push toward greater transparency and more honest communication about deep space risks. One force is journalism. Investigative reporters who dig into technical documents, interview researchers, and connect dots can bring hidden information to public attention. Some excellent journalism has been done on NASA's challenges, though it competes for attention with more celebratory coverage. Another force is whistleblowers. Individuals within space agencies who believe the public is being misled can speak out. This has happened occasionally. Engineers who raise concerns about shuttle safety, researchers who question official risk estimates. But whistleblowing has professional costs, and it remains rare. A third force is the scientific community. Researchers who study spaceflight, health, radiation, biology, and related topics can publish findings that contradict official optimism. They generally do. The technical literature is full of concerning findings, but translating technical papers into public understanding requires intermediaries who may not exist. A fourth force is accident. Nothing focuses attention on risks like disaster. If a deep space mission fails catastrophically, if astronauts die in a way that reveals the inadequacy of safety measures, the gap between internal knowledge and public messaging will be exposed. This is a terrible way to achieve transparency, but it has happened before. A fifth force is changing institutional culture. If NASA leadership decided that honesty about risks was more important than maintaining optimism, the agency's communication could change. This would require leaders willing to accept short-term costs for long-term benefits, a rare quality in any institution. Each of these forces operates weakly compared to the institutional pressures toward optimistic communication. Change is possible, but not assured. The gap between what NASA knows and what NASA tells may persist for years or decades. Now let me consider what individuals can do, what you, as someone who has now learned about this gap, might do with this knowledge. First, you can inform yourself more fully. The technical literature is available. NASA's own reports document the risks in detail that public communications omit. You can read the studies, understand the uncertainties, and form your own assessment. Second, you can demand better communication. As a citizen and taxpayer, you have standing to expect honest information from public agencies. You can contact elected representatives, participate in public comment processes, and advocate for transparency. Third, you can support journalism and research that exposes the gap. Media organizations that invest in investigative coverage of space programs, researchers who publish inconvenient findings, whistleblowers who speak out, all of these need support and protection. Fourth, you can engage in the public deliberation that transparency enables. If you conclude that Mars exploration is worth the risks, advocate for it honestly, acknowledging the dangers, but arguing that the benefits justify them. If you conclude that the risks are too great, advocate for alternative approaches, robotic exploration, risk reduction research, or different priorities entirely. The point is not to oppose space exploration. It's to ensure that decisions about exploration are made honestly with full information through democratic deliberation. This is what NASA's current communication practices don't fully enable. Now, Let me bring this exploration to a close by reflecting on what the gap between knowledge and communication reveals about human nature and human institutions. We want to believe in progress. We want to believe that challenges can be overcome, that the future will be better than the past, that human ingenuity can conquer any obstacle. This optimism is valuable, it motivates achievement, sustains effort, and makes difficult endeavors possible. But optimism can also blind us to reality. When we want something to be true, we're inclined to believe evidence that supports it and discount evidence that contradicts it. This is human nature, and it affects institutions as much as individuals. Space agencies want to explore the cosmos. They want their programs to succeed. They want to maintain funding and public support. These desires are legitimate, but they create bias, a tendency to see the path forward as clearer than it is, the risks as more manageable than they are, the timeline as shorter than it is. This bias is not malicious. It's not even conscious, for the most part. It's the natural result of motivated reasoning applied to institutional communication. People who work at NASA genuinely believe in the program and genuinely see the challenges as surmountable. Their optimism is sincere, even if it's systematically tilted. The result is a gap between what they know intellectually and what they communicate publicly, not because they're hiding information, but because they frame it differently, emphasize different aspects, and draw different conclusions than a more neutral observer might. This is the human condition. We all do this. The question is whether we can recognize it, correct for it, and create institutions that push back against it. Space exploration is too important to be conducted in a fog of optimism. The decisions we make about human spaceflight, whether to proceed, how quickly, with what safeguards should be made with clear eyes, full information, and honest assessment of the risks. Currently, they're not. The public is given a rosy picture that obscures the dangers. Policy decisions are made based on optimistic timelines that technical reality doesn't support. Astronauts are sent into harm's way with risks that aren't fully quantified or communicated. They know it's deadly. NASA knows, ESA knows. Every space agency that has seriously studied deep space exploration knows that the risks are greater than public communications suggest. They know that the solutions are inadequate, that the timelines are unrealistic, that the astronauts they're planning to send face dangers that haven't been fully disclosed. This knowledge creates responsibility. If you know something is dangerous and you don't warn people adequately, you bear some responsibility for the consequences. This applies to institutions as much as individuals. I'm not suggesting that NASA is culpable in some legal sense. The agency operates within a complex political and institutional environment, facing pressures that make honest communication difficult. The people who work there are doing their best under difficult circumstances. But I am suggesting that the current situation is not acceptable. The gap between knowledge and communication is too large, the stakes are too high, and the public deserves better. What would better look like? It would look like NASA telling the public what it tells its researchers, the full scope of risks, the magnitude of uncertainties, the limitations of countermeasures. It would look like timelines that reflect technical reality rather than political aspiration. It would look like genuine public deliberation about whether deep space exploration should proceed and under what conditions. This would be harder than the current approach. It would risk public support, complicate political decisions, and force difficult conversations about acceptable risk. But it would also be more honest, more democratic, and more respectful of the public that funds these programs and the astronauts who fly them. Deep space is not a theme park. It's not a frontier waiting to be conquered by can-do optimism. It's an environment that is fundamentally hostile to human life, where the risks are extreme and the margin for error is zero. We can still explore it. Humans have always ventured into dangerous environments, accepting risk for the sake of knowledge and discovery. But we should do so honestly, with clear understanding of what we're getting into. What NASA refuses to tell you about deep space is that they know it's deadly. They know the risks are greater than they acknowledge, the solutions are less effective than they claim, and the timelines are more uncertain than they suggest. Now you know too. What you do with this knowledge, whether you accept the current situation or push for change, is up to you. The cosmos awaits. But it awaits honest exploration conducted with clear eyes and full hearts, not exploration built on optimistic narratives that obscure the dangers. They know it's deadly, and now, so do you.